Welcome back to my channel. Today we are diving into a machine learning case study that hits close to home. Literally, we are going to look at the how a random forest classifiers was used to predict air quality index category using data like pollutant level, temperature, and wind speed. This matters because millions of people around the world have no idea if the air they are breathing right now is safe or not safe. And this kind of model could change that. By the end of this video, you will understand the problem, how model was built, what results it got, and what it means for the real world. Let's go. Okay, let's start with the big picture. Air pollution kills around 7 million people every year, according to the World Health Organization. I mentioned it here. And that's more than malaria, tuberculosis, and AIDS diseases could die people in each year combined. Can you imagine that the four diseases cause literally lower than the air pollution kills count? And the air quality index or AQ is a number scale that tells us how clean and pollutant the air is. It has four main categories and they are good, moderate, unhealthy, and hazardous. Good means safe for everyone, and moderate means acceptable for most people, and unhealthy means harmful for sensitive groups, and hazardous means dangerous for entire population. Right now, measuring AQ accurately requires expensive sensor network and monitoring station. Many cities, especially in developing countries, should not afford this. So the question this case study asks, can machine learning model classify AQI level using basic atmospheric measurement without needing a dedicated monitoring station? That exactly what this random forest model was built to do. Total models was trained on 1200 city days observation. You can see here. And each row represent one city on one day, combining data from UCI air quality data set and OpenAQ global records. Each observation has 9 inputs. You can see here. PM 2.5, PM 10, NO2, SO2, CO03. And PM 2.5 is fine particulate matter, which these are the tiny particles so small they can enter your bloodstream. And PM10 is cursed dust particles. NO2 is nitrogen oxide from cars and factories. SO2 is sulfur dioxide from power plants. And CO is carbon monoxide from vehicle exhaust. O3 is ground level ozone. And three weather features are temperature, humidity, and wind speed. And lastly, the targeted value is the AQI category: good, moderate, and unhealthy, hazardous, which is seen in already. And one important note is this is a 4-class classification problem, harder than the typical yes or no binary prediction. The class distribution was roughly 30% good and 28% moderate, or 25% unhealthy, and 70% hazardous. So you can think why random forest I am choosing. Let's get a quick recap. A random forest built hundreds of dedicated decision trees, each trained on different random slice of data. Then it combines their votes for final prediction. This makes it more accurate and more stable than any single tree like decision tree algorithms. For this multi-class problem, the model was set up with 150 decision tree, slightly more than usual because there are 4 output classes we need to find, and max depth of 12, deep enough to capture complex pattern without overfitting, and balanced class weight. So the model does not ignore the hazardous category just because it has fewer examples. And features selected using is square root of 9 input, about 3 features per 3 splits. Can you catch up with me? And these settings were tuned using 5-fold cross validation, the gold standard for finding the best model configuration without overfitting to the test data. Okay, I already explained most of it, and let's go to the numbers calculation. The model was tested on 240 unseen city days observation. Here how it compared against 2 baseline matrix: accuracy, precision, recall, F1 score, and the ROC. AUC is the overall rate. Random forest 85.4%, and Decision tree, see 76.2. It is drastically changed, right? And in logistic regression, 71.8. Just like you can see every one of the numbers here, and random forest win every matrix by the significant margin. And ROC, AJ, you can see the average overall points. It is 0.921, which is accurately, I think 92% it will perfectly correct for 4 class problem. That excellent distributive ability across all 4 AQI categories. In this point, the biggest takeaway from the error, most miscalculation happened between moderate and unhealthy, which makes sense because those two categories sit right next to each other on the AQI scale and can have very similar pollutant reading on boundary line days, right? Okay, let's move into the future importance analysis. Here we can see what makes random forest extra helpful. It tells which future actually matter for the prediction. And here's the ranking. You can see PM 2.5. It is 30% importance, strongest driver of poor air quality. By far, the most important thing is fine particles are the first driver of poor air quality globally. And ground level ozone, 80% important, dangerous in summer heat, causes respiratory damage. And NO2, 50%, a direct signature of vehicle traffic and industrial activity. PMO, 12%, cause dust, significant in dried and arid cities. And CO, 8%, urban vehicle exhaust marker. And then SO2, temperature, humidity, and winds follows in decrease in importance. Wind speed actually ranked last, and this makes initiative sense. Higher the wind disperses pollutant across a wider area. Lower local AQI reading, but the wind itself does not produce pollutant, right? The model correctly learns the pollutant concentration or what really determine AQ. This alignment with the environmental science knowledge validates that the model learns real pattern, not noises. Can you understand? Okay, till now what I'm saying is the full of my case study, and let's wrap up. This case study shows that a random forest classifier can predict AQI categories from atmosphere measurement with 8.54 accuracy, and a overall rate is 0.921, which is literally good and beating both decision tree and logistic regression by the wide margin. The key takeaways are PM 2.5 is the dominant predictor of air quality consistent with the WHO and the EPA environmental guidelines, and a visible method shines on multi-class problem like this one. And meteorological data alone isn't enough. Pollutant concentration are what drive the most model, and this kind of model can provide low-cost AQI estimate for cities that lack monitoring infrastructure, enabling earlier public health warning. The and Everyone's are thinking every model has its limitation, right? And in this limitation, the models was trained on city data following as US EPA AQI standards. So it may need retraining for religions using different scales, and adding time-based features like hours of days or seasons could push accuracy even higher. And that's all for the case study breakdown. Air quality is one of those problems where machine learning can genuinely make a difference, especially for communities that doesn't have access to expensive monitoring equipments. If you find this video useful, that's all I need. Thank you.